I'm Kenneth Owens, formerly of Google, currently at Brex. And this is Janet Ko, still at Google. We're two of the co-chairs of SIG apps, and co-chairs are really just in SIG's kind of an administrative burden. Like we organize meetings basically in that function. We're also two of the tech leads, and I think we're the set of people that are both chairs and tech leads. So that means we're code owners for the workloads APIs. There's another one right there. He's from Red Hat. You can yell at him later. So for the SIG apps deep dive, we usually do a couple of things. One, we try to make it interactive, and we want to hear about like, your opinions on what the SIG should be doing. Two, we try to teach. So we're going to start with going over some of the code that we actually maintain in tree, and some of the code that we maintain out of tree inside of SIG apps, basically to give an overview of how to write controllers. Then at the end of it, we're going to point to the work that needs to be done in the community and ask you to contribute. And talk about that a lot. Try to get your opinions on how we prioritize it as well. If there are any questions as we go, please feel free to be interactive.
Yeah. So this is our agenda. So I'll start with walking through the workload controller internals. So we picked 3 of the workload controllers to just give you, do a code walkthrough to help new contributors or existing contributors to understand the controller code structure. So I'll start with the basic reconciliation loop of a controller. So for a given controller in Kubernetes, we usually have the desired state and then the current state. And based on that, we make some changes. And we keep doing that in the loop. And this change is level triggered, which means that we're not looking at the diff between the diff in the state. We're just looking at the current state and what's the expected state in the resource spec. So let's take deployment controller as an example. So to give you a quick recap on what deployment does is that it creates replica sets, and replica set then create pods. And deployment supports a feature called rolling update, so you can rolling update your containers by changing the spec of a deployment. And then what it does internally is that it will scale up and scale down replica sets. And let's take a look at the source code of that. Okay. So that's probably too small. Is it good enough? Okay. So let's start with this piece. So all the controllers are just part of the Kubernetes controller manager. We ship it as a binary, and deployment controller is one of them. And all the controller code lives in the package in the Kubernetes repository. You can find it under package/controller. And under there one of it is deployment, and you can see other controllers here. So if you go inside the deployment controller code, you can see the new deployment controller. That's the start of this whole controller code. And let's talk about a bunch of things in this controller. First, let's talk about something called shared informer. So you can see that we pass some parameters into this deployment controller, and it's using a framework in Kubernetes that's called shared informer. So what it does is that the controllers can use that to receive notifications of the changes to the resource. For example, if I have the deployment informer, I can get the events, the notification of the creation, the update, or deletion of a deployment. And from there, I can access a shared cache. So this is not required for all controllers. It's just an optimization, because without this, then you'll need to keep making requests to API server, and it doesn't scale as you can imagine. So instead of that, we have this informer framework that allows you to receive notification on updates, and you can update the cache, and then you only read or list from the cache in the controller. And it's called shared informer because this cache can be shared among different controllers. And then one of the caveats is that when you write code in controller, you should never, ever mutate objects in the cache, because when you do that, it will affect other controllers that's also reading from this cache. So when you get resource from the cache, if you need to make some changes to it, you just do a deep copy. And then when you do the copy, don't forget to not do shallow copy, because there's resource like annotations, which is a map. If you do shallow copy, you can still mess up with others' code. And then if you scroll down here, so you can see that I have the D informer is the deployment informer, and then replica set informer, and the pod informer. That just means that the deployment controller cares about these resources. And then underneath here, there's something called sync handler. It's just the real business logic in this deployment controller. So after it receives some events from all those resources that it watches, it will try to sync the deployment. And the sync is just the loop that I mentioned here. Okay, and then we have something called work queue. So you can see here, there's a function called in-queue deployment, and there's in-queue. So what does the in-queue mean? It means that we are storing the deployment resource in a queue. We call it work queue. It's another framework in Kubernetes. So the benefit of using that is that you can queue all the changes that you need to make you can queue the changes to a resource, and then you can work on that later in the reconcile. In this case, it's the sync deployment. So you can have multiple workers that takes resource from the work queue, and then you can reconcile it by running sync deployment later. And this work queue will make sure that no two deployments will be operated by the same worker at a time. And then, so in here, you can see that when we run this controller, it will start some workers, and you can specify how many number of workers you want for this controller. And then you can see it's running this thing called worker. And then if you scroll down, there's a function called sync deployment. That's the sync handler thing that I just mentioned. Okay, so now we have the sync deployment that has all the real business logic of this controller. And you can see that we first got a thing called key. The key is just an index in the work queue for you to find this resource. And the controller, the deployment controller just used the namespace and name as a key to find this deployment. This works because we only store deployment in this work queue. We don't store other kinds of resource. So if you have multiple kinds of resource, then you'll need a different function to define key for this work queue. And then we can scroll down a little bit. You can see that I'm getting this, I'm finding this, given this key, I'm finding this deployment from the key. I'm splitting the namespace and name from the key and then get the deployment. And note that this is listing from the cache, so we're not directly talking to API server. And then we got the deployment from the cache, and we don't want to mutate it by accident, so we call this deep copy here. And then let's see if there's anything interesting. Here, if the deployment deletion timestamp is not nil, that means that this deployment will be deleted. So we don't need to reconcile it anymore. We don't need to create or scale up, scale down replica sets. We just need to sync the status of it. So we can just return sync status only. And then scroll down, there's a function called check if it's paused. So in deployment controller, when you pause a deployment, you can stop the controller from doing the rollout. But then when you pause a deployment, we still allow you to scale up or scale down the deployment. But in order to do it safely, the scale up or down will be proportionally. For example, if you have 2 replicas of the old pods and then 3 replicas of the new pod, then if you want to scale it up by 2 times, then you need to scale them proportionally. So that's safer because you don't want to suddenly roll out the new replicas too quickly. And then if it's rolled back, so we have a feature called rollback in deployment, but it's now deprecated, but we still keep it here for backward compatibility. And then finally, here, if it's a scaling event, even if the deployment is not paused, we run the same function to scale it proportionally. And the last piece is that finally we can do the deployment rollout. So deployment supports 2 different types of rollout strategy. The first one is the recreate. That means that I will delete all your old pods completely. And after all those old pods are deleted, you can create new ones. And then for rolling update, it's just rolling up and scaling up and down old ones and new ones. So that's it. And because there's a lot of details here, but after this walkthrough, it should be pretty easy for you to dive deeper into deployment. And then let's go back to here. The next controller that I want to talk about is Replica Set, because it's related to deployment. And what Replica Set does is that it just creates an n number of identical pods from a pod template. And then the source code lives here. It's under package controller Replica Set. And then an interesting, so I can show you the basic of this Replica Set controller, but you can see that a lot of code is very similar. For example, it also has the informer framework, and it also has the sync handler, and it's listing from the cache. And one thing that's particularly interesting in Replica Set controller is that it has something called expectations. And if I scroll down to the sync, let's find the sync handler using Replica Set. Okay. So if you scroll down to the business logic of Replica Set, you can find that it's using something called expectations. Let me find it. Where is it? Oh, yeah, you can see that it's doing something like deleting expectations, creating expectations. So expectation is a pair of atomic counters for you to track the creation and deletion of resource. And in this case, Replica Set controller is using this to track the creation and deletion of pods. And you can also find it in other controllers like jobs and daemon set. And why do we need this? Why don't we need it in deployment controller, for example? This is because that if you still remember, we are reading from cache. And the cache could be outdated when you read it. So imagine that when the Replica Set controller creates, for example, if it's told to create 3 pods, and then in the next sync loop, it's looking at the number of current pods in the system and doesn't find those 3 pods because the cache hasn't been updated. So the Replica Set controller will then try to create 3 more pods. So this problem will eventually be reconciled, but you don't want that to happen too often. So to solve this problem, we have the expectations. So with this expectations, you can say, in this loop, I expect, for example, 3 more pods. And then the controller will not be synced until the expectations are met. So you can set a counter to creation equals to 3. And then when the controller observes that the pod is being created from the informer, from the event, then every time it will check the expectations, like I saw this expectation, I saw this creation. And then after 3 creations, the expectations will be satisfied. Then the sync replica set can be executed. So in the replica set controller, there's also something called filtered active pods. And we have this because we don't want, for example, if there's a node that cannot, a node that no pod can be scheduled, then, or maybe there's a race condition, then the kubelet may reject the pod to be scheduled on that node. So the pod will be failed. But then if replica set doesn't ignore that pod, which is failed, then it will have less number of active pods forever. So to compensate that problem, we ignore the inactive pods. And finally, the real logic lives in the manage replica set, manage replicas. And in this function, it just create and delete pods based on the expectations. So for example, it calculates how many pods it needs to create. Then it will set that I expect creations and then tell it which replica set expect this creation and the number of creation it expects. So the next one will be stateful set. Let me hand it off to Ken to talk about it.
So the skeleton for stateful set, like we already saw setup code for replica set and deployment. It's basically the same as deployment and replica set. You can think of stateful set as the controller with increased guarantees and lowered expectations. As Janet was saying, with Replica Set, we're trying to get a heuristic number of pods running, but you can go past that scaling point, right? And you can be under at any point in time. The guarantees of stateful set are, we're gonna give you no more than this many pods running. So if you have a stateful set with 4 replicas, we're never gonna give you 5, right? We're gonna give you 4 replicas, or at least attempt to, with names that you can actually recognize and that you can find inside of DNS. And we'll do storage provisioning for you. In some ways, it made the controller a lot simpler. In some ways, it got a little bit more complex. So, that's just a skeleton code. The interesting pieces in stateful set are actually in stateful set control. Yeah. So, at the top, these things, controller revisions. This was an interesting problem. So, replica set came first, right? This is just a way to give you a fungible number of replicas of the same pod, made pod useful. What was deployment really about? Deployment was about having low disruption updates for your replica sets, for your app, right? So inherently in deployment, when I'm scaling this replica set up and scaling this replica set down in order to do a rolling update, if I need to do a rollback, a low disruption rollback, all I'm doing is scaling the other direction. So it became a problem of looking at the template of the replica set and saying, oh, well, this replica set actually implements the declarative intent of the current intent of the deployment. So instead of doing a rollover and creating a new replica set and just wiping everything, which is usually what you don't want when you're doing a rollback at 2 o'clock in the morning, we'll actually say, oh, well, this replica set's already halfway up and it already matches the spec. So we're gonna scale this one up and then scale this failing one down. Now, stateful set doesn't have an intermediate representation like replica set. It works directly on pods. So we needed a way to achieve the same thing. Hence, controller revision. Now, I think the daemon set and stateful set are still the only actual in-tree controllers that use it. But if you are writing your own controller and you need a way to solve that problem, to store off the declarative intent that you can detect later in order to do graceful rollbacks, you can use this object, and it's in-tree. So what we're doing at the top right here is we're actually just, so if you go to this, all we're doing is we're pulling down the previous revisions of the stateful set that have been stored. And then we have a comparison function that tries to detect equality between the existing revision and the stateful set's pod template. So here we're just getting the current revision of the stateful set, the update revision of the stateful set, and the collision count. So the current revision basically is, here's the controller revision that realizes the declarative intent of the user at this point in time. The update revision is, this is what the user is requesting. Actually, let me rephrase that differently. The update revision is saying, here's what the user wants now. The current revision is saying, here's what I'm currently trying to reconcile. So the current revision is what the stateful set controller thinks the previous declarative intent of the user is. The update revision is the version that you've declared immediately. So truncate history. Truncate history is basically doing the same thing that, say, cron job controller does with its jobs, or what deployment does with replica sets. We can't store an unbounded number of controller revisions. We can't store an unbounded number of replica sets. We can't store an unbounded number of jobs, though we used to, in all cases. And at any rate, so what this is doing is it's just going through the history of controller revisions and saying, okay, well, for what you've declared in the template, in the spec of the stateful set, we're going to bound the list of controller revisions that you can possibly roll back to that number. And it just truncates them and deletes the ones that are no longer there. So this is the most interesting function. So can you guys hear me, by the way? Is this loud enough? Okay, cool. All right, the volume seems to go up, down. At any rate, so with update stateful set, what we're doing is we're going to look at the current revision, and we're going to look at the update revision. we set the generation, update the number of replicas, and now we check the pods. So this is where things get hairy, right? So for stateful set, we have to actually sort the pods in the ordinal order, right? And there are two different rollout strategies that we support. So the first strategy, which was the original one, was ordered ready. Ordered ready is what you would want to do. Like, let's say you're running something like MySQL, right? Or let's use Postgres. People, that's popular these days. Everyone hates MySQL. Everyone loves Postgres. So let's say you're rolling out Postgres, and you actually want to set up a replication topology. If you were using stateful set to do this, one way you can do it using a little bit of duct tape and spit, you roll out pod 0, that'll be your master. When you roll out pod 1, you pass the ordinal into that pod. You have a configuration script that says, okay, I'm pod 1. I'll go look at pod 0. That's going to be my master by default. And I'm going to put myself into the replication chain there. And then you set up the replication topology that way. Ordered ready was meant to support that type of rollout. It's still used in like Vitesse, for instance, which is based primarily on MySQL. They use stateful sets, and I'm pretty sure they still use ordered ready policy to roll up their replicas. They do sharded and replicated. Cockroach, I believe, still does the same thing with theirs as well. Cockroach is like Postgres Vitesse, kind of. It actually does some cooler stuff with level DB under the hood, but same thing. For other things like Zookeeper, you don't need it. So for Zookeeper, allow burst would be true, right? So when allow burst is true, all of that kind of goes out the window. You don't get ordered ready anymore. Instead of doing ordered ready, it's just going to go ahead and throw them all out there at once simultaneously. Zookeeper doesn't care. Like, there's a well-known theorem that basically you can't do leader election in an anonymous ring anyway. So they all have to be configured with an ID, and they have to be configured with network coordinates of their peers, right? So you throw them all out there, and they will pretty much just figure it out. I think the default Kafka stateful set from Confluent actually still does ordered ready. I think they still do ordered ready for Zookeeper, but one of the things I've pushed on them, and what I do personally in production, is turn it off and just do burstable, because generally Kafka figures it out, and generally Zookeeper figures it out. The bigger problems with Kafka and stateful sets are more along the lines of when I elect my broker, and then I do the other thing that stateful set does, which is roll and update. I can have many, many, many leader elections and switch that broker leader over again. That's kind of one of the big problems with stateful set today. We don't have a way of saying, kill this specific pod. We always say, we go in reverse order of the pods that we rolled out. Anything else interesting? So the is terminating function. So the other thing about stateful set is, like, and this you can't turn off. I'm actually probably loud enough I can just yell. But the other thing about stateful set is that if you get a terminating pod in the middle of a rollout, so let's say I roll out pod 0, I roll out pod 1, I roll out pod 2, I'm not going to move to pod 4 until pod 3 is up and ready, right? Now, burstable allows me to bypass that for the purposes of turning them up and tearing them down. But when I'm doing a roll and update, I'm never going to bypass that. The thinking behind that is like, okay, sure, if you're going to go and turn them all up, and you're saying just do it all at the same time, you know you've got Zookeeper, you know you've got Kafka, we're going to let you do that. It makes sense. Updates need to be more controlled. And that's basically just old school Google. Always, when you're doing a rollout, do it gradually. Don't just go gung-ho with it. Let's see. Oh, shit. What was the... Hey, could we get a time check? Yeah.
You have 5 minutes.
Okay. All right. So we plan on talking about a whole bunch of other stuff. But this is the relevant stuff with stateful set. I mean, basically, it is most interesting in contrast to deployment. And we knew we didn't have time to talk about daemon set, which is based on node selectors. So there are a bunch of other things we want to talk about in terms of contributions that we were looking at going forward in 2019. But, I mean, we only have 5 minutes left, so are there any... I'd also like to give you guys time to ask questions. Well, I'd also like to give you guys time to ask questions if you have any, or to like drive any discussion that the audience will. yeah. If we had more time, we'd actually plan to talk about the current state of the application. CRD is GA, I believe, or is it, did we do beta? No, it's beta, but it's fully released.
Beta.
It's still being contributed to. We were going to use that as an example of how you can use Kubi Builder to build your own controllers out of tree. One of the takeaways, like the two takeaways we wanted you to have are, here are controllers, here's how they work, and here are the things you should think about if you're going to contribute to the in-tree controllers. We also wanted to get to, here's how you do out-of-tree controllers, because the way the SIGs are working right now, we're more than willing to take and shepherd contributions that live out of tree. And the general direction from SIG architecture is that we'd like to really do everything out of tree if possible. Like, we'd love to get deployment, we'd love to get daemon set, and those core controllers and how they live as sub-contributions that we just suck into the binary for a release. Like, that's the dream. Whether we get there or not is another story. But for newer stuff, we'd love to do it out of tree. And like the application CRD, if you want to go look at the code, provides one example that SIG apps owns of how you can do that.
So for deployment rollback deprecation, it's not about the feature. It's not working. It's mostly because the controller is doing something that's sort of anti-pattern. So how the rollback is done is that you set a rollback to which revision in the controller spec, in the deployment spec. And then the controller will then change the pod template in the spec to the older version. So the controller itself is mutating on the deployment spec, which is not what we recommend people to do, because the spec should be changed by users. So we're thinking how we can implement this better, so we deprecate this feature just for that reason. And I want to say something that I forgot to mention earlier about the expectation. So why we have that in Replica Set instead of having it, but not having it in deployment, is because when deployment creates Replica Sets, it creates Replica Set with a name generating a hash from the pod template. So the name is always deterministic. But when Replica Set generates pod, the pod name is just a random string. So that's why we need the expectation.
So what do you mean by the atomic configuration?
A year ago, deployments let you atomically roll out and roll back things, but config maps and secrets don't work that way. It's really hard to explain to users why that's broken. Right?
So I mean, this goes back to like, if you guys have ever seen this stuff on declarative application management that Brian wrote and put on GitHub, how do you do declarative application management with config maps and secrets that are stored in GitHub? There have been a lot of things that have been done in kubectl in order to generate config maps and send them up, right? Like the general advice is, if you look at, so Janet had a proposal out, it's about a year ago now?
More than a year, I think.
So getting that to the API machinery was kind of tough. We implemented the garbage collection for jobs.
Yeah.
I think we have a contribution for pods.
Yeah.
Config maps and secret garbage collection is the way we kind of recommend you do it. What it means is, like, when you generate a new configuration map or a new secret from the get-go, you should generate it such that it's unique and immutable, right? Like, every time you update a config map, you're not updating the existing one. You're not pushing it down to the downward API because, God, that would be an uncontrolled release. That's unimaginable. Like, I mean, literally 1,000 pods all randomly start picking up what changes to a configuration map in production simultaneously. Wow, that's so much fun. Just create a new one, update the deployment to point to it. Now you have a new problem. I have a config map chain that goes back forever. How do I delete them? How do I reconcile them? So we are still kind of trying to push forward with API machinery for a way to do this in tree that allows for a garbage collection.
Mm-hmm.
The answer today is, what I personally do is I implement my own Reaper, and I just have something that sits there and watches the configuration maps, knows that if it's older than this, it's garbage, and just deletes it. Which is like, you know, as a maintainer, it's not like, yeah, he just told me to, basically go jump off the bridge. Those are the realistic solutions that we have today, but it is a problem we're still working on.
Yeah. I'm trying to. How do we fix it?
I mean, you can go back to API machinery and say, like, look, this is still a real problem. This is how we do it. The other thing we can do is if we want to implement the garbage collector as a community project that's outside of True, right? Because the main objection was to putting this in the existing garbage collector, which is a graph-based controller, which we did not cover in this. It is a much deeper conversation.
Fair enough.
Yeah, but we could always do that as a SIG sponsored or a non-SIG sponsored project out of True.
I think, sorry.
If we're going to start pushing for external controllers and stuff, that might be a good solution to a lot of that feeling problem. But then we got to get back into the release somehow. Does that be medium admin, add-on manager? Yeah.
Add-on manager is a good way to do that. What it comes down to is as we have more add-ons and as we have more open source contribution that isn't built in, we expect that, like, yeah, you turn on EKS or GE and you're going to get your base API machinery, but you'll be able to use your own controllers and you stand up your own, and you're looking at it like that's kind of gross.
The problem is that with an application developer hat on, if the core features aren't there, then none of the development is sort of relying on the API, right? We have to come up with a core that everybody can share with some of this functionality into it.
So I think there's some work in CLI for the prune.
For pruning, yeah.
Yeah.
So pruning is one way to do it. So there's that, and then there are open source. So like if you look at Weedflux, they actually, I think maybe about 6 months ago, implemented usable prune logic for some of this stuff. Right? Some of this does exist in the open source. It's just a very fine balance between like what do we as Kubernetes maintainers put in tree as a built-in, and what do we depend on the open source community for? We try not to solve problems that are already being solved elsewhere, right?
But everybody's solving the same problem over and over again. So it's really
We try to take those things and put them in tree, right? And so like, I mean, this is good feedback that we should maybe take the SIG architecture from that.
Oh.
And it's a problem that we do see being solved in the community, but it's also one of those problems that everybody is solving independently over and over again. So we can add a lot of value by bringing it in tree. Like it is a fine balance. Like I think, do you remember one-time class ended up going in tree?
One-time class?
Runtime class, the thing that allows you to
Oh.
configure different containers like gvisor.
Mm.
Yeah, it was alpha. So that we actually wanted to do that out of tree. There's a lot of stuff we've been trying to do out of tree, and it's just I don't have really good hard answers for like, here's the clear guideline for when it goes in tree and when it doesn't. But I think your thesis says like as a SIG apps, we should go back to SIG architecture and say, well, I mean, we should just do this. I've taken that as an action.
Just want to ask a quick question on, right now, with Replica Set, restart policy coming, you said always, I know there's like a big conversation that GitHub as well.
Mhm.
Answer for that one, is that a choice, or is that just like a big decision, on failure, never, restart policy, also on issues, let it know, stuff like this, has study, and some of the maybe some of that connection to the issue on that particular node, and that also pressing on that, whatever.
So I think there are some controllers that has restart policy set to always because we expect those controllers to be used to run the services that should always run, never finish. So we have jobs that don't have restart policy as always.
Yeah,
So
for jobs it's different.
Yeah.
To answer your question, there's this project within SIG scheduling called Descheduler. And as one of the reasons for Descheduler is to be able to, one, rebalance your cluster evenly if you're scaling up or down. Or, I'm not sure if that's fixed, but there is a plan for having it fixed. That if your pod is in a crash looping for whatever reason on a particular node, it will get evicted and it will go through again a scheduling phase, which might fix the problem. Currently, if a pod gets scheduled once, it will never get scheduled again. That's why the descheduler is only doing evict from a node and go through a regular scheduling once again and see if it works.
If I can add to that, concisely, we will probably never make the core workloads controllers that run services anything other than run always. The run always is actually capturing the user's declarative intent. And don't get me wrong, we could be moved from this, but like you'd have to have a real clear story about what it means to have a service that runs to completion. Like batch workloads run to completion, stateless serving workloads or stateful storage servers don't run to completion. And to add on to more to what he said, like there are still troubles in terms of like mediating interaction between the scheduler and the controllers. That's something that we definitely want to focus on going forward. It's not clear right now, like, so for instance, what is it, security policies, right? So I can declare security policies inside of a replica set that will get scheduled onto a node that don't support the security policy that I've configured, right? Like, that's a bad thing. Right now, our answer is don't do that. We need a better answer there, right? So figuring out how to deal with that is currently a topic that's in flight. So no, we probably won't do anything but restart always, but yes, we are continuing to address and be concerned with the general interaction between the components, the core components of the cluster, and trying to improve that experience. Okay, so now shilling for the SIG. We meet every Monday, if you guys aren't aware.
Every other Monday.
Every other Monday now. 9 a.m. PT.
Yeah.
We have a Slack channel. We have a community page. If there's any other questions you want to ask, feel free to come to the meeting and ask them. If there's any contributions you want to make or get started on, it's a great place to kind of come and check out. If, yeah, just come and say hi if you like.
Yeah.
Thank you.
Thanks.